All right, so next page is just a series of like function transformations. Again, this should be kind of like review, right? So the kind of like the key thing, the way that I kind of understand these things is, am I affecting the x or am I affecting the y? If I'm adding, subtracting, manipulating the x in some way, since x is the domain, right? We know x represents the domain of a function. Anything that affects the x, like this, or this, or this, or this, all of those things are going to affect the domain of the function in some way. Whether it's a shifting of it, whether it's reflecting of it, whether it's a stretching or condensing of it, they're going to affect the domain. Whereas since f of x represents the range, anything that is just affecting f of x, not the x inside the f of x, that's going to end up being a range change. Right, so I'm affecting the f of x, so I'm adding some value to it. I'm multiplying all of my y values by something. I'm negating all of my y values. Right, so this is what each of these things do. Again, should be some sort of review for you. I doubt this is the first time you've ever walked into like function transformations. So this is kind of also why I like Taylor's form of a line. It reinforces how transformations affect a function. So there were three different things that I could do here. So three different transformations that are going on. So the first transformation, if you think order of operations, is what's affecting what's happening inside of parentheses, right? So this x minus x sub 0. So I'm subtracting x sub 0 from x, right? So this is going to be a domain change. We're affecting the domain in some sort of way. So the first transformation is we move the line, because we're just talking about a line right now, left or right. If I just thought about a boring line, right? So if I have just y equals x, this f of x equals x, right? So it would look something like that. The first thing that happens is we take this this line, and we just shift it to the left or the right some amount. So you might get something that looks like that. So transformation 2, right? So if we think PEMDAS, right, multiplication comes next. So that multiplication is next, this slope. So what is it doing? It's multiplying my now function values, my range change by something. So this is going to be a vertical compression or stretch. So that's what the slope does, right? If this was my original function and I multiplied every value of y by like 7, we're now going to get a much more rapidly approaching line. We haven't changed this left or right shift, right? I'm just taking my function now, it increases faster. I'm stretching it vertically. And then finally, our last transformation, this addition, right? So I'm adding on to a function. I'm adding on to my kind of y values now. So this is going to be a vertical shift. All right, so I'm going to take my function here. I'm going to maybe shift it up 3 units or something like that. Who cares how much I shift it up? But everything's going to move up 3. Right, so now that original y-intercept is no longer the original y-intercept. It's moved up 3 units, right? Everything shifts up 3. So that's what Taylor's form of a line does, right? It kind of maps the transformations that our function takes. A couple of other things that are also important about slope that we'll kind of see throughout. So if lines are parallel to one another, you know the slopes are equal. If two lines, so let's draw first just in case, parallel, so they look like that. If two lines are perpendicular, perpendicular means that they're meeting at a right angle. So they would look something like this. So we could see instantly that unless the lines are vertical and horizontal, if two lines are perpendicular to one another, this kind of blue one will always have a positive slope, or this blue one right now has a positive slope, the red has negative. But if I make the blue have a negative slope, the red has a positive slope. We could also see that if my blue line starts to increase quicker, my red line starts to decrease in kind of like an inverse way, right? So one gets big fast, one gets kind of like small. So this would be kind of inverses of one another. So if two lines are perpendicular, they have, say, opposite signs. And they're also reciprocals of one another. Reciprocals of one another. So if this blue line has a slope of, say, 5/7. This one right here would have a slope of -7/5. The reciprocal of 5/7 is 7/5, and then they also have to have opposite signs. If we have a horizontal line, the equation of a horizontal line is just y equals to a number. So if I had just something like this, right, that perfectly flat line, well, it's not positive, it's not negative, it's what's in between positive and negatives. This is a slope of 0. And if I have a vertical line, now vertical line, if we try to do the slope formula, right, so the change in x, we'd have some change in y, there's some rise, but there's 0 change in x. If we divide by 0, we say that the slope is undefined. And so those are our slopes that we'll deal with throughout the course.